Good day, everyone. Let us continue our discussion on intelligent systems about image processing. So, here's the outline of our presentation. Now, we will define symbolic learning, the overview of image processing, the traditional methods in image processing, introduction to AI in image processing, neural networks in image processing, deep learning for image enhancement, and symbolic AI in image processing. No? So this might be long, but I promise you it is short as usual. You will just watch another videos for the remaining slides. Okay? So ano ba ang image processing? Okay? So image processing in AI symbolic learning refers to the manipulation and analysis of digital images using algorithms to extract meaningful information or enhance visual quality. Napaka-basic lang naman ito. Pag may mga pictures kayo, if it is blurred or medyo malabo, i-modify nyo siya, i-edit nyo siya, that's what you call image processing. But with the aid of AI, iba na ang kanyang meaning. In case here, there are now algorithms to make sure that you extract meaningful information, okay, or enhance its visual quality. Okay, so that's image processing in AI. To further understand, here is the video.
Welcome to our Vision Campus. Today I will focus on image processing. There are endless situations calling for image processing done by software. In general, they can be clustered into a few groups: checking for presence, object detection and localization, measurement, as well as identification and verification. In most cases, the acquired image from the camera is not directly processed within the application. Instead, it is pre-processed to enhance the image according to the specific task. Examples of pre-processing are noise reduction, as well as brightness and contrast enhancement. Some of these steps can be done directly by the camera itself and thus save CPU load on the host side. To use the camera as a measuring device, it must be calibrated to the physical world. Camera calibration can actually refer to two things: geometric calibration and color calibration. With geometric calibration, we correct the lens distortion. Furthermore, we can also determine the relationship between camera's natural units, meaning pixels, and the real-world units like millimeters or inches, for example. With color calibration, we ensure an accurate reproduction of colors. The better the pre-processing, the better the image quality and the results of the image processing within your application. Now let's have a closer look at image processing. When it comes to locating parts, usually matching is involved. This means looking for regions that are similar to or the same as a predefined template. This template can either be also an image or a geometric pattern which contains information regarding edges and geometric features. These methods are called correlation pattern matching and geometric pattern matching, respectively. Let's have a look at cookie inspection. Your template would be the image of a perfectly shaped cookie. A camera takes images of all cookies on the conveyor belt. As soon as there's a cookie that doesn't match the template, the cookie is rejected. The main use of measurement with the help of image processing is in alignment or inspection applications. Most measurement techniques rely on edge detection algorithms. An edge is an area in an image displaying significant change in the image intensity, or in other words, a high local contrast. This means your software analyzes the gray levels of the image and based on this identifies shapes, measures distances and calculates the geometry. This measurement and calculation is made possible by the camera calibration that establishes the relationship between pixels and real-world units. Take the label of a bottle, for example. With measurement, you can check if the label has been placed correctly. Typical applications for identifications are barcode and 2D matrix code reading, or optical character recognition, also called OCR. One way to manage optical character recognition is by separating the characters in the image and comparing them with a set of templates. Afterwards, the software can convert the captured data into editable and searchable data. A popular example for OCR is automatic number plate recognition, also known as ANPR. Each of these processing techniques covers a wide spectrum of machine vision applications, but combining them can give you even more possibilities. Imagine a car is entering a parking garage. A camera takes an image of the license plate and the car. When the car is exiting the garage, the camera takes another image. Then the software compares those two images. The gate only opens when the license plate and the car model are the same as in the first image. This was only a short overview of the information you can gain from your images by using image processing, but it offers a taste of the many different possibilities. Thanks for watching.
Okay, so that's how image processing works with the aid of AI, no, in today's setup or situations. So here are some of the importance of AI in image processing, sorry. So we have here the feature extraction, pattern recognition, and image enhancement. Okay, when we say feature extraction, image processing aids in extracting or pagkuha of relevant features from images, facilitating subsequent analysis and decision making. So dito, meron kayong i-upload or meron kayong ipapakita sa image sa inyong equipment or sa AI, sa inyong device na images wherein with image processing, it will now extract relevant, important, significant features from those images that will now help you or help the company or you in decision making and analysis. Okay, that's feature extraction. Okay, second one is pattern recognition. Okay, when we say pattern recognition, it is pre-processing images. AI systems can better recognize patterns and objects within visual data. Okay, dito naman sa patterns, for example, nakita nyo yung cookie kanina, di ba? Na dumadaan sa conveyor belt. So doon, yung pattern kasi na nandun is puro bilog dapat, di ba? Once na meron siyang makitang irregular shape, no? Di ba, gagawin niya. Alisin niya yon, i-extract niya yon kasi hindi naman yun ang nandun sa system na kailangan mag-proceed sa kanyang output, ba? So kung ang pattern niya is puro circle, and then there's an object na may problema naging square, no? Hindi siya palalagpasin doon. So it is now that AI, no, can recognize patterns. For example, sa bilog, di ba? Nakikita niya, that's image processing, using pattern recognition. Okay? The third one is image enhancement. Image processing techniques improve image quality, no? Making it easier for AI models to interpret and understand visual information. Okay? So when you say image enhancement, in-upgrade, in-improve, in-develop, it is making the quality of an image better, no? For that, to make sure that AI can be basically interpret and understand the visual information. Okay, so those are the importance of image processing in AI, feature extraction, pattern recognition, and image enhancement. So overview of image processing. Again, image processing, image processing involves manipulation, okay, of digital images using algorithms, to enhance visual quality, extract information, and or perform analysis. So that's basically image processing. So here are some of its major applications, no, yung image processing. We have here medical imaging, remote sensing, and security and surveillance. When we say medical imaging, no, image processing is used for tasks like tumor detection, organ segmentation, and medical image reconstruction. So dito, bibigyan ka ng iba't ibang images, no, or scans, and then ipaprocess ito ng device with the use of image processing. Makakita siya magkakapag-detect siya ng iba't ibang problema. For example, dito yung tumor, di ba? Nakita kung saan yung area, kung ilan yung circumference niya, di ba? Same time, it can also help in medical image reconstruction. So that's the application of image processing in medical sector or health sector. Next one is remote sensing. When we say remote sensing, no, in satellite imagery, image processing techniques are applied for land cover classification, disaster monitoring, and environmental analysis. Okay, so image processing kasi, ginagamit ito nga ng mga uh, for remote sensing in such a way that may magpapalipad ng drone or through satellite, they will capture various land areas wherein they will classify it according to their land cover. For example, pag pinicture mo isang area, may makikita ko doon na puro green. Then, ang magiging classification mo ngayon doon is forest area, di ba? Same time, kung meron something blue in that area, that could be a body of water. Okay? The same time, if there are some irregularities in water bodies and area, no, they could easily monitor if it's prone to disaster. For example, flooding, no, landslide, no. It can also be used for environmental analysis, yung mga image processing. Kasi, for example, meron kang na-capture na data and medyo malabo, no? I-enhance mo siya. Yun naman ang purpose ng image processing. Enhance visual quality to make sure that you can extract relevant information and perform, again, analysis based on that captured images. No? So that's remote sensing. No? The third one is security and surveillance. No? Image processing, is vital for tasks such as face recognition, object tracking, and anomaly detection in surveillance systems. So dito, the image processing natin, basically, common na ngayon sa mga cellphones yung merong face recognition, di ba? Nagamit natin ito to unlock your devices. It's one way of securing your devices with the use of your facial features, di ba? You can also use these for object tracking. For example, yung mga cameras natin, they can now easily detect plate numbers dun sa mga populated areas, sa mga traffic jams, traffic vehicles, sa mga sasakyan. So that's the use of image processing in security and surveillance. They can now basically process images based on that gathered or captured image, then enhance it visually. So that's some of the applications of image processing we have in the health sector, medical imaging. Next one is remote sensing, and the last one is security and surveillance. Okay, ano bang importance or significance nito? Image processing and AI. So basically, we have three: the improved analysis, enhanced visual quality, and automation. When we say improved analysis, no, image processing enables the extraction of valuable insights from visual data, enhancing decision making in various domains. So that is improved analysis, no? Kasi pagka na-enhance or na-process natin yung images, no, you can now have the ability to extract important data, no, based on that visual data na enhanced, no, that will now aid you in decision making. No? So marami naman purpose yung mga images natin in decision making. So that's improved analysis. You can now easily analyze various aspects of various sectors. Okay, that's improved analysis. Next one is enhanced visual quality. When we say enhanced visual quality, by removing noise, mga unnecessary image, unnecessary noise, and artifacts, image processing techniques improve the clarity and interpretability of images. Kasi meron mga images na there are noise. When we say noise, yung mga extra objects sa pictures na pag in-enhance mo is mawawala. Same time, it can remove unnecessary objects that is irrelevant sa mga images. No? It can then sharpen your images. It will now provide a better understanding on the images presented. Okay, so that's enhanced visual quality. Okay, the third one is automation. When we say automation, automated images, no, or automated image processing workflows streamline tasks like image restoration, object detection, and image classification, increasing efficiency and productivity. So these are the significance of it, no? Improved analysis, enhanced visual quality, and automation. To further understand again image processing, let us watch this video.
We're in this new era of AI-powered image processing. AI has pervaded all branches of image processing, including image recognition, image restoration, and enhancement. In addition to influencing image generation, we are using AI increasingly for predictive analytics on images. AI has tremendous potential to transform healthcare, particularly radiology. In the specific context of molecular imaging, I'd say AI is really improving image quantitation. We are seeing images that are AI generated that have enhanced resolution and reduced noise. We're also seeing a lot of potential for AI-assisted clinical decision making, including new tools for diagnostics, therapeutic outcome evaluation, and theranostics. So this is a very interesting session with a fabulous lineup of talks covering a whole bunch of different emerging topics that highlight applications of AI in nuclear medicine. We'll see a variety of different talks, for instance, that cover radiomics, new hybrid machine learning approaches for radiomics as applied to Parkinson's disease. There will be talks on AI methods for attenuation correction in both PET and SPECT. We're also going to look at new approaches for AI-based image denoising and even kinetic modeling for dynamic PET. In terms of takeaways, I would say the session sort of highlights the sheer breadth of applications where AI is really making a difference in nuclear medicine. In addition, there is also this focus on methodological advances. We are seeing a lot of increased emphasis on techniques that rely on self-supervised and unsupervised AI approaches, and also on hybrid approaches that not only rely on data, but also on physics.
So now let us continue our discussion on traditional image processing techniques. Ano bang problema dito sa traditional na to, no? So when we say traditional image processing, no, it involves operations like filtering, thresholding, and morphological processing to manipulate and analyze digital images. Napaka-tight din ito or napaka time consuming, ano? So, ano ba ang challenges na meron sa traditional methods? Okay? We have here three, no, problems, challenges, no? Limited adaptability, manual tuning, and lack of context awareness. When we say limited adaptability, traditional techniques may struggle with complex image content or variations in lighting conditions, leading to suboptimal results. No? So when we say limited adaptability, It depends on the image content and the lighting conditions, of course, no? Since ano to traditional or manual, no? With that, medyo mahirap ang mag-extract ng data and makapag-provide ng magandang result. So that's limited adaptability. Okay, next one is manual tuning. When we say manual tuning, it is designing effective image processing pipelines, often requires expert knowledge, and manual parameter tuning, making the process time consuming. When you say manual tuning, ito yung depende ka sa ibang tao to improve the quality of your image. Kasi kumbaga sa pintor, titimplahin niya yung image, no? Titimplahin niya kung ano bang magandang feature ang meron doon to make sure that you can extract important details or valuable data, no, from the image. So that is manual tuning. The last one is lack of context awareness. Okay, when we say lack of context awareness, no, there may be lack of ability to incorporate contextual information, limiting their robustness in real world scenarios, no. So kapag kasi hindi natin maintindihan yung images, we cannot extract or we cannot integrate the idea or the context information, no. Hindi natin alam kung meron ba siyang relation sa real world scenarios, no. Meron ka nakitang blue, meron ka nakitang brown na triangle, no? If you don't know, kung medyo nasa manual tuning tayo and we are not aware of that exact image, di natin alam na meron palang ano doon, na yung blue is you can consider as sky, yung triangle is mountain. So, kung di natin alam yon, medyo mahirap tayo mapag-provide ng information, no, sa traditional. But when ngayon kasi yung mga image processing natin with the aid of AI, they can now easily provide contextual information regardless of kung gaano karami yung naibigay mong information or data. Okay? So again, these are the limitations and challenges that traditional techniques we have experienced, no? Limited adaptability, manual tuning, and lack of context awareness. So again, ano bang role ng AI sa advancing ng image processing? We have here feature learning, semantic understanding, and automation. When we say feature learning, no, AI algorithms can automatically learn, no, features from raw image data, improving the effectiveness of image processing tasks. So, since AI is meron na siyang vast amount of data or images, it can now easily learn kung ano ba yung pictures na meron siya, images na meron siya. From there on, they can now improve their processing or they can easily draw features from those images, no? Improving the effectiveness of image processing tasks. Okay, so that is feature learning. The second one is semantic understanding. When we say semantic understanding, no, AI, no, AI models can understand the meaning of visual content, enabling more accurate and context-aware image processing. No? So, kung kanina, mapapansin niyo yung lack of context awareness, hindi niya maintindihan kung ano bang meron sa image na to, no? Sa traditional, pagdating sa AI, no? They are now aware ano ba ang meron sa visual content, ano ba ang meron doon sa image na yon, no? Enabling them to make or to provide more accurate and context-aware image processing, no? So that is semantic understanding. The third one is automation. When we say automation, no, AI-based image processing workflows automate tedious tasks like image segmentation, object recognition, and content-based image retrieval. So here are the three roles of AI in advancing image processing: feature learning, semantic understanding, and automation. Okay? Ano ba ang benefits? Okay? Ano ba ang benefits ng paglalagay or pag-integrate ng AI sa images processing? So we have here three ng benefits. enhance accuracy, scalability, and adaptability. When we say enhance accuracy, okay, AI techniques, no, okay, often outperform, no, traditional methods in terms of accuracy and generalization to diverse image datasets. So, kasi pagka nasa traditional method nga tayo, medyo time consuming siya. At the same time, medyo matagal kasi kailangan pa ng manual tuning. With the aid of AI, they can easily provide accurate data or accurate image quality, di ba? Same time, with the set of large data sets, they can provide again accurate output, no, from the image presented. Okay. Second one is scalability. AI models can scale to large volumes of image data, di ba? Pwede silang matuto ng mas marami pang images, di ba? Making them suitable for high throughput image processing applications. So again, when you say AI, they learn from vast amounts of data. In this case, they learn from vast amounts of images. Okay, so with those amounts of images, they can also suitable to for a high throughput image processing application schools. So kung regardless of how bulky or gaano man karami yan, with the aid of AI, they can easily process those kind of volume na throughput sa kanilang mga AI systems. So that is scalability. Okay. The third one is adaptability. When you say adaptability, no, they can easily adapt and learn from new data again, di ba? Natututo kasi yung AI natin from various data na input sa kanya. So with the help of it, AI algorithms can easily adapt and learn, no? And allowing image processing systems to continuously improve over time, no? So yung kasing mga images na kanyang nare-retain sa kanya, it can use it for a better way of producing output, no? Kasi yung mga data na meron siya, it will now then provide or allow the image processing systems to improve, no? Regardless of gaano man siya katagal, yung image na is nagagamit niya pa rin to with its large amount of images. It will now then allow the image processing systems to continuously improve over time. Okay, so those are the benefits of integrating AI images in processing. We have enhanced accuracy, scalability, and adaptability. So now again, let us study the various neural networks in image processing. We have convolutional, recurrent, and generative adversarial networks. So ito is we have already discussed it previously. So to further understand it, convolutional is specialized in again grid structured data images. Para dito yan, yung CNN. The other one naman is recurrent neural networks. It is suitable for processing sequential data for text and speech recognition. Okay, convolutional naman is for images, di ba? Mas fit siya sa mga images. And generative adversarial networks, it provides generating realistic images and data by learning from training set. So again, let us watch the following videos I have prepared for you to watch.
The terms computer vision and image processing are used almost interchangeably.
Okay, pop quiz. What am I drawing? I'm going to make 3 predictions here. Firstly, you think I drew a house. You'd be right. Secondly, that it just came really easily to you. It was effortless. And thirdly, you're thinking that I'm not much of an artist. And you'd be right on all counts there. But how can we look at this set of geometric shapes and think, oh, house. If you live in a house, I bet it looks nothing like this. Well, that ability to perform object identification that comes so easily to us does not come so easily to a computer, But that is where we can apply something called convolutional neural networks to the problem. Now, a convolutional neural network, or a CNN, is an area of deep learning that specializes in pattern recognition. My name is Martin Keane, and I work in the IBM garage at IBM. Now, let's take a look at how CNN works at a high level. Well, let's break it down. CNN, convolutional neural network. Well, let's start with the artificial neural network part. This is a standard network that consists of multiple layers that are interconnected, and each layer receives some input, transforms that input to something else, and passes it as output to the next layer. That's how neural networks work. And CNN is a particular part of the neural network, or a section of layers. Let's say it's these 3 layers here. And within these layers, we have something called filters. And it's the filters that perform the pattern recognition that CNN is so good at. So let's apply this to our house example. Now, if this house were an actual image, it would be a series of pixels, just like any image. And if we zoom in on a particular part of this house, let's say we zoom in around here, then we would get, well, the window. And what we're saying here is that a window consists of some perfectly straight lines. Almost perfectly straight lines. But you know, a window doesn't need to look like that. A window could equally kind of look like this, and we would still say it was a window. The cool thing about CNN is that using filters, CNN could also say that these 2 objects represent the same thing. The way they do that then is through the application of these filters. So let's take a look at how that works. Now, a filter is basically just a 3x3 block. And within that block, we can specify a pattern to look for. So we could say, let's look for a pattern like this, a right angle in our image. So what we do is we take this filter, and it's a 3x3 block here. We will analyze the equivalent 3x3 block up here as well. So we'll look at, first of all, these first group of 3x3 pixels, and we will see how close are they to the filter shape. And we'll give that a numeric score. Then we will move across 1 column to the right and look at the next 3x3 block of pixels and score how close they are to the filter shape. And we will continue to slide over or convolve over all of these pixel layers until we have mapped every 3x3 block. Now that's just for one filter, but what that will give us is an array of numbers that say how closely an image matches our filter. But we can add more filters. So we could add another 3x3 filter here, and perhaps this one looks for a shape like this. And we could add a third filter here, and perhaps this looks for a different kind of right angle shape. If we take the numeric arrays from all of these filters and combine them together in a process called pooling, then we have a much better understanding of what is contained within this series of pixels. Now that's just the first layer of the CNN. And as we go deeper into the neural network, the filters become more abstract, or they can do more. So the second layer of filters perhaps can perform tasks like basic object recognition. So we could have filters here that might be able to recognize the presence of a window, or the presence of a door, or the presence of a roof. And as we go deeper into the CNN to the next layer, well, maybe these filters can perform even more abstract tasks, like being able to determine whether we're looking at a house, or we're looking at an apartment, or whether we're looking at a skyscraper. So you can see the application of these filters increases as we go through the network and can perform more and more tasks. And that's a very high level basic overview of what CNN is. It has a ton of business applications. Think of OCR, for example, for understanding handwritten documents. Think of visual recognition and facial detection and visual search. Think of medical imagery and looking at that and determining what is being shown in an imaging scan. And even think of the fact that we can apply a CNN to perform object identification for badly drawn houses. If you have any questions, please.
What do you do if the patterns in your data change with time? In that case, your best bet is to use a recurrent neural network. This deep learning model has a simple structure with a built-in feedback loop, allowing it to act as a forecasting engine. Let's take a closer look. Recurrent neural networks, or RNNs, have a long history, but their recent popularity is mostly due to the works of Jürgen Schmidhuber, Sepp Hochreiter, and Alex Graves. Their applications are extremely versatile, ranging from speech recognition to driverless cars. All the nets we've seen up to this point have been feed-forward neural networks. In a feed-forward neural network, signals flow in only one direction from input to output, one layer at a time. In a recurrent net, the output of a layer is added to the next input and fed back into the same layer, which is typically the only layer in the entire network. You can think of this process as a passage through time. Shown here are 4 such time steps. At t equals 1, the net takes the output of time t equals 0 and sends it back into the net along with the next input. The net repeats this for t equals 2, t equals 3, and so on. Unlike feed-forward nets, a recurrent net can receive a sequence of values as input, and it can also produce a sequence of values as output. The ability to operate with sequences opens up these nets to a wide variety of applications. Here are a few examples. When the input is singular and the output is a sequence, a potential application is image captioning. A sequence of inputs with a single output can be used for document classification. When both the input and output are sequences, these nets can classify videos frame by frame. If a time delay is introduced, the net can statistically forecast the demand in supply chain planning. Have you ever used an RNN for one of these applications? If so, please comment and share your experiences. Like we've seen with previous deep learning models, by stacking RNNs on top of each other, you can form a net capable of more complex output than a single RNN working alone. Typically, an RNN is an extremely difficult net to train. Since these nets use backpropagation, we once again run into the problem of the vanishing gradient. Unfortunately, the vanishing gradient is exponentially worse for an RNN. The reason for this is that each time step is the equivalent of an entire layer in a feed-forward network. So training an RNN for 100 time steps is like training a 100-layer feed-forward net. This leads to exponentially small gradients and a decay of information through time. There are several ways to address this problem, the most popular of which is gating. Gating is a technique that helps the net decide when to forget the current input and when to remember it for future time steps. The most popular gating types today are GRU and LSTM. Besides gating, there are also a few other techniques like gradient clipping, steeper gates, and better optimizers. When it comes to training a recurrent net, GPUs are an obvious choice over an ordinary CPU. This was validated by a research team at Indico, which uses these nets on text processing tasks like sentiment analysis and helpfulness extraction. The team found that GPUs were able to train the nets 250 times faster. That's the difference between 1 day of training and over 8 months. So, under what circumstances would you use a recurrent net over a feed-forward net? We know that a feed-forward net outputs one value, which in many cases was a class or a prediction. A recurrent net is suited for time series data, where an output can be the next value in a sequence, or the next several values. So the answer depends on whether the application calls for classification, regression, or forecasting. In the next video, we'll take a look at a family of deep learning models known as the autoencoders.
Recurrent neural networks, or short RNNs, are an essential part in deep learning. They are widely used and are incredibly effective in many different kinds of applications, especially in the field of natural language processing, like for text generation or text classification, but they can also be used when working with images or video data. So in this video we learn what RNNs are and how they work. This video is part of the Deep Learning Explained series by Assembly AI, which is a company that creates a state-of-the-art speech-to-text API. And if you want to try their API for free, then grab your free API token using the link in the description below. And now let's get started. First, let's have a quick look at one definition of RNNs. RNNs are a special class of neural networks that operate on sequence data and allow previous outputs to be used as inputs while having hidden states. So let us reiterate. They are also neural networks. They have something to do with hidden states, and they can keep track of previous outputs in a sequence. So if this definition is not clear for you right now, don't worry, we will come back to this in a moment. But first, let's have a look at why RNNs work so great. And for this, we look at one example. Let's do a quick test and complete this sentence. The color of the sky is blue. Or another one, I grew up in Germany, that's why I'm fluent in German. And I bet you guessed the correct word, because for our brains it should not be a problem to determine the missing word. And we know the word because we know the previous text. We don't just look at one word and throw away the previous information. We remember the previous context and then use this information. And this is exactly what RNNs do. So if we try to do this word prediction with a normal neural net, then this would not work, because one major shortcoming of neural nets is that they cannot keep track of previous outputs. And this is what RNNs try to fix. Now let's go back to the original definition. By now it should be more clear what is meant with sequence data and previous outputs. For example, a sequence data can be a sentence where the RNN looks at each word separately, encodes it to a mathematical representation, and can then remember the previous outputs. But how exactly does this work, and what are these hidden states? So a normal neural net gets an input, then has different hidden layers and returns an output. Now RNNs have loops in them, allowing the information to persist. So we can also unroll this loop and look at this picture in a different way. We can now interpret this as a sequence data with different time steps. We have the first input where we do calculations in the hidden layers and can then get an output. And then we pass the information from the hidden states onto the second time step. And here again we get an input, then we do calculations where we now can use the previous information, and then again can get an output and pass on the information, and so on. Now each time step contains the information from all previous steps, so the last step has information about all the previous context. And then, for example, we can use this very last output here and pass it on to a simple linear classification layer and do the word prediction like in the example from before. So by now I hope the explanation and motivation of RNNs is clear to you. Another reason why RNNs are so powerful is because of their flexibility. Now, normal neural nets or convolutional nets have the limitation that they don't remember previous states, and moreover, they accept a fixed size vector as an input and produce a fixed sized vector as an output. For example, one image can be the input and the probability of different classes is the output. So this is what we get with traditional neural networks, and recurrent neural nets, on the other hand, operate on sequence data. So they operate over a sequence of vectors, and this could be sequences in the input, the output, or in both. And this allows for many different applications. For example, we can have a one-to-many relationship, which can be used for music generation. So we get one input, but many outputs. We can also have a many-to-one relationship. So we have many inputs, but only one output. This is, for example, used for sentiment classification. And we can have different types of many-to-many relationships. For example, here for name entity recognition or for machine translation. And by the way, these images are taken from the Recurrent Neural Networks cheat sheet that you can find on the official Stanford website. And I will put the link in the description for you. Now, how do RNNs learn? And basically the same as other neural nets, they learn by the backpropagation algorithm, and to be more specific, by backpropagation through time. So we do a full forward pass through all the time steps, and then a full backward pass through the entire sequence and calculate the gradients. So nothing really special here. And by the way, if you want to learn more about backpropagation in detail, then we have another video for you on our channel that we link here. Now, this long way of traveling can have one major problem. The more layers we have to travel through, the more multiplicative gradient calculations we have. And this can lead to a so-called vanishing gradient or also to an exploding gradient. And this in turn means that these information get lost and it gets difficult to capture long-term dependencies. So the more time steps we have, the less information we can keep from time steps that are further in the past. So let's again have a look at the two sentences from the beginning. The color of the sky is blue, and I grew up in Germany, that's why I'm fluent in German. In the first example, the relevant information are sky and blue, so they are close together. But in the second one, maybe we can guess the word should be a language because we see the word fluent. But to guess the correct language, we also have to read the previous sentence. So we have to go further back in time. So the more we have to go back, the more difficult it can be for our RNN because of this problem with the vanishing gradients. But luckily, there are existing solutions that tackle exactly this problem. Long short-term memory, or LSTM, and gated recurrent units, or GRUs, are two special variants of RNNs. They are capable of learning long-term dependencies using a mechanism called gates. So they often outperform simple RNNs and are important to know, but getting into more detail here would be too much for this video, but I'm sure we will cover them in a later video in the series. But also having these two improvements does not mean that simple RNNs can be skipped, because on the downside they are computationally much more expensive, so in many cases a simple RNN will be just fine. Now at the end I also want to quickly show you how you can use this in code. So both deep learning frameworks PyTorch and TensorFlow make this pretty easy for you because they have existing layers that you can use. For example, here is the PyTorch code. So here you can set up this RNN layer and you find this in the torch.nn module. And the same way you will also find the LSTM and the GRU layer. And then what is important to note is that when we call this layer in our forward pass, we also have to put in a hidden state. So here we initialize the hidden states with a zeros tensor, and then we pass it to our RNN layer. And then we get two things back. One is the output and one are the encoded hidden states. So yeah, this is how it works in PyTorch, and in TensorFlow the API looks different. But here again, you have the layers already available. For example, you can use the simple RNN, or also LSTM and GRU are available. and then you can put this in a, for example, a sequential model. Alright, I hope I could explain RNNs in a simple way. If you still have questions, then let me know in the comments. If you enjoyed the video, then please leave us a thumbs up and consider subscribing to our channel. And then I can recommend to watch this video if you haven't already about backpropagation, and then I hope to see you next time. Bye!
So in this video, let's learn about recurrent neural networks, how they work, how they learn, and also some of the improvements that were made on them over time. So let's get started. A nice thing to do before to start talking about RNNs is to remember how neural networks look like. So if you remember, in a normal neural network or a deep neural network, you can call it, we have an input layer, a hidden layer, and an output layer. And information runs sequentially. So first the information comes to the input layer, then it is passed to the hidden layer, and then finally the output is produced. So all of the data points that you have, you give them at the same time, all of the features of your specific data point that you're training on. The difference in neural networks of recurrent neural networks is that they are recurrent. So that means that the same thing happens over and over again in a way. So this is what a recurrent neural network looks like when it's unrolled, and I will also show you the rolled form. But basically what you need to know is that each of these little sections are actually one of the same. They're the same network, or they are the same neurons. So what happens is these are all the different input features, and you give them one after another. So you first give the first feature of your input, and output is calculated and also passed to the second time step. We call them time steps. And then the second feature of your input or a data point is given, including the output of the first one. Another output is calculated, and so on and so forth. So when you put it in, when you show it as it is actually, and how it is that it is just one unit. So what happens is you give it an input, output is calculated, but at the same time output is passed again. The second feature of the input is given. So when you compare it to neural networks, what happens is in neural networks you give all of the features at the same time, whereas in recurrent neural networks you give all of the features one step at a time. So it is basically things happen in a time step manner. So we would call this the first time step, the second time step, third, fourth, and fifth time step. So basically in each of these time steps, except the first one, you have two inputs. One of them is the output from the previous time step, and one of them is the input of this time step. So how do we calculate the output of recurrent neural networks? Well, we do it with this formula. It's actually quite simple, even though it looks like a complicated math formula thing. You have weights for your inputs. So for each time step, you have the weights. And for all of the outputs from the previous step, you have another set of weights. And you also have the biases. All of this is of course passed through an activation function, and at the end you have the output of your recurrent neural network. One thing to understand here is that even though it looks like we have many steps, as I said, it's actually just one unit. So Wx and Wy, which are the weights of the output of the previous layer and the input of this layer or time step, is the same because they're actually the same. Here we're just showing them in an unfurled way because it's easier to understand. So there's only one set of weights for the input and one set of weights for the output. So there is a very common way of showing cells of RNNs, because these cells here, how the output is calculated, can be different. And we will talk about different types of cells too. But let's talk about how to depict a simple RNN cell. So what we normally have, of course, as we talked about, the output from the previous time step, and the input of this time step. So these T's basically depict this time step. T is this time step, T minus 1 is the previous time step. So to show this formula on a diagram, we can say, okay, there is a multiplication happening here. This is multiplied with Wy, and here another multiplication, and this is multiplied with Wx. And then we also add the bias here, so that's why the crosses and the pluses here. And this all goes through an activation function, of course, and very commonly what's used is the hyperbolic tangent function. But of course you can use other things too, but generally hyperbolic tangent function is the one that is being used with simple RNNs. And at the end we pass the output of this time step to the next time step, and also we output it. But sometimes this is not the case. So for simplest of RNN cells, this is the case where you pass the output to the outside world and also to your next time step. But sometimes you do an extra step on before you output something. So you maybe pass it through a softmax function if you want it to be between 0 and 1 instead of -1 and 1, because that's what the hyperbolic tangent function will produce. Then basically what you pass to the next state will not go through the softmax function, that extra step, and then you will still pass it to the next function, next time step. So it still is the same thing, but has seen less processing. So then what happens is we call this the hidden state of this time step. So the hidden state of this time step is passed to the next time step. So this is just a interesting difference to keep in your mind, that you do not always just pass the output that you get to the next time step, but sometimes you call it the hidden state. There are, of course, a bunch of ways how you can use this architecture, because you do not always have to pass all of your output all of the outputs that you calculate in your cells. So let's look at a couple of different options. The first type is sequence-to-sequence RNN model. So basically for every input that you give in each time step, you get an output for that time step. And for these kind of things, you can use for things where you're forecasting things. So for example, price forecasting or stock exchange forecasting sort of things. The second one that you can use is called sequence to vector. Sometimes it's called sequence to single, because you only get one output at the end of the whole RNN network that you have. And these things that you use for, let's say you have a sentence or you have an email, and at the end of or as an output of the model, what you want to know is it scam or not? Or for example, sentiment analysis, like what kind of sentiment does it have? Is it negative or positive? That kind of things. So for that, in each time step, you give your network a input, and then you just ignore the outputs. Even if it's producing the outputs, you do not look at them. The only output that you look at is the one at the end, because before seeing the whole sentence, your model cannot come to a conclusion, of course. Another one that you have is vector to sequence, or as I said, single to sequence. By the way, the reason that they are not called single but vector here is that because the output that you have is in the form of a vector most of the time, and it is not just a single number. That's why we just call it vector instead of single, but both ways are fine. So in vector to sequence sort of architectures, what you're doing is you're giving the network one input, and you are letting it output a sequence of things. So this could be, for example, you give your network an image, and then you're having it output a explanation of that image word by word. So let's say you give a photo of a dog running on a beach. Then for each of these time steps, the network will output a dog running on the beach, for example. So those are the kind of things that you would use a vector to sequence architecture for. And lastly, we have encoder-decoder sort of architecture. So in these kind of architectures, RNN architectures, at first you are only giving your network inputs. So input for a couple of time steps, or how many ever that you need. And then you get outputs. So, and then in the second part, you only get outputs. You do not give any inputs. And these kind of architectures are good for translation, because to translate a sentence, your network needs to see the whole sentence first, because meaning of some words might change, the translation of some words might change if you see the whole sentence based on the context. So that's why you first give it the whole sentence, and then you give get the translation word by word on the decoder part. All right, but how does RNNs learn? So how does the training work? It's actually quite simple. It's very similar to normal neural networks that do not have any interesting architecture, but we just call it backpropagation through time. So what happens is the output of the network is calculated, of course, and we do it you can think of it as like its unrolled form. So at first you give it input as 0, and then, or the hidden states from the previous time step, because it doesn't exist as 0. You give the first input, you get a first output. You give the second input, you get a second output. And then you just calculate whatever you want to calculate. And then we calculate the cost of this network. But as we said in the previous slide, sometimes the network, how you use the network might change. So you might want to ignore the first couple of outputs, or maybe you're just interested in the last 2 outputs, or maybe even you're just interested in the last one. So based on that, the cost is calculated. And then based on that, as we did with normal neural networks, we calculate the gradient, and then the gradient is passed back through the network, and the weights are updated. But as we said, all the weights of all of these time steps are actually the same because they're actually one time step. And then the gradients are calculated as we do with normal neural networks, and then these gradients are passed back in the network to update the weights. But as I said, you might ignore some of the outputs while you're calculating costs, so the gradients are passed back only through the ones that you used in the cost calculation. So RNNs are actually really good for analyzing sequential data, so this could be time series data, text, or audio files, for example, but of course they have some shortcomings. So the first one is that they have unstable gradients. And you can imagine that, right? Because it's a very long sequential sort of architecture. So the further back you go in this architecture, the smaller your gradients are going to get. So you might not be able to update the weights on the previous timestamps in a way, or to previous time steps in a way that will be helpful for the whole network. What you can do for this problem in RNNs is use other techniques that we use for normal neural networks too, or just deep neural networks too, to deal with unstable gradients. Or you can use layer normalization instead of batch normalization, because batch normalization is not as effective with recurrent neural networks. So they're kind of tricky to apply to recurrent neural networks. So instead you can use layer normalization. And another problem with simple RNN cells is that they forget. If you give it a very long sentence, it tends to forget what was being said at the beginning of the sentence. So the applications that are created with it are not really effective, or they don't work as well. So instead we have the LSTM or GRU cells that we can use to make sure that we still remember the beginning of a sentence at the end of it. So let's see what a LSTM cell looks like. If you remember how I showed you in that diagram, the RNN architecture, the simple RNN cell looks like, it will be easier to understand this one here. So what we have is a couple of sigmoid activation functions, and then we have another hyperbolic activation function. And we here see that there are two hidden states that are passed from the previous time step to us. And then we again pass those two different hidden states to the next time step. And then we again have an input, and then we have an output. So let's look closely what all of these things mean. So the first things that we need to understand here is that, as I said, we have two hidden states coming and going to the previous and next time steps. The first one is the previous one, as we talked about, is just a hidden state from the previous step. But the other one, C, is a long-term memory hidden state. So basically, as you say, there are less things happening to this hidden state, and we either forget or add some things to this long-term hidden state, and it passes to the next time step without much coming out of it or going into it. Why do I know, or how do I know things are being added or extracted from these time steps? Well, because we have the forget gate here, we have the input gate here, and we have the output gate here. So basically these are the gates that create the information workflow, or how this information is used in this specific time step. So let's talk a little bit more in detail about that. So what we have here are called gate controllers. So anything other than the hyperbolic tangent function, we call the gate controllers. And what the gate controllers do is they either input 0 or 1. And in this way, they determine if something is going to be forgotten, if something is going to be input, or if something is going to be output from the long-term state. And how this works is basically in the forget gate, we decide which part of the long-term memory should be removed from the long-term memory. So, we're saying, okay, this can be forgotten now. We don't need to understand, we don't need to remember this information anymore. In the input gate, we decide which part of the hidden state or the information that we just added to the hidden state needs to also be passed on to the long-term memory. So we're deciding, okay, actually this piece of information is important to remember later. And in the output gate, we decide which part of the long-term state we need to extract from the long-term state right now and use as an output, either as in the hidden state to pass on the next timestamp, or as an output in this, or as part of the output that we generate in this timestamp. So it sounds kind of complicated, even though it's sort of intuitive that there is one long-term memory, one shorter term memory, and then we either forget things from the long-term one, either use it or add new things. and it's kind of confusing to understand, okay, but like how does this thing whole work? Why do we forget input, or how does the forgetting and inputting happen? But you don't have to understand everything behind it. You don't have to understand how it's all working. Basically, what you need to know is that it is working, and this is the intuition, and I think that will get you where you need to go. So you don't have to obsess over how this whole works. So another different kind of cell that we have is called the GRU cell. GRU cell is basically like a simplified version of the LSTM cell. You know, you have less things happening here. You do not have a separate output. As you can see, the hidden state that is passed to the next time step, and the output is exactly the same. And here the gate controller R decides which part of the previous state will be shown in the main layer. So main layer being the one where we pass through the hyperbolic tangent, and basically the main state that is being passed to the next time step. The R decides which part of the previous state that we got from the previous timestamp is added to the timestamp, and the output of this, or the state and the output of this timestamp. And that's it. That's kind of like a first step at RNNs, kind of beginner level information that you need to know. If you want to learn more about RNNs and deep learning in general, go check out my course, Deep Learning 101. I will leave the link in the description below. Before you leave, don't forget to give me a like and maybe even subscribe to show your support. I would also love to hear your opinions about this video or any questions that you have in the comment section below. But for now, thanks for watching, and I will see you in the next video.
So let us continue on the deep learning algorithms for image enhancement. When we say deep learning algorithms, no, it utilizes neural networks, no, yung mga napanood natin kanina, no. When we say deep learning algorithms, it is being used to improve, no. It uses deep learning algorithm uses neural networks to improve the visual quality, no, of images by removing noise, enhancing details, and adjusting brightness and or contrast. Yun lang naman ang purpose ng mga ng AI or ng learning algorithms, no, to improve the visual quality, no. Paano ba ini-improve yung visual quality, no? Removing noise, enhancing details, and of course, adjusting brightness and or contrast, no. So we have here examples of deep learning architectures. We have here the autoencoders, GANs again, and super resolution convolutional neural networks. When we say autoencoders, no, it learns to reconstruct clean images from noise inputs by encoding the image into a lower dimensional representation and then decoding it back to the original space. So basically, parang ito yung from PNG to JPEG. So nag-improve yung quality, but it lowers the original tawag dito, size. So that's basically that autoencoders. No? Next one is GAN. No? It is basically it generates realistic images with the help of various inputs. Okay. The third one is SRCNN. These are designed to enhance the resolution of low resolution images by learning high frequency details from training data. So dito, ini-improve natin yung mga resolutions ng mga images using sa mga data inputs na meron din yung AI. Okay? So in image processing, symbolic AI involves the use of logical rules and representations to analyze, to interpret visual data. Symbolic learning complements deep learning by providing interpretability, explainability, and domain-specific knowledge integration. For example, in medical image analysis, symbolic AI techniques can incorporate expert knowledge about anatomical structures and disease patterns to assist deep learning models in accurate diagnosis and treatment planning. So before we end this slide or this presentation, let us watch our last video.
The terms computer vision and image processing are used almost interchangeably in many contexts. They both involve doing some computations on images, but are they really the same thing? let's talk about what they are, how they are different, and how they are linked to each other. Image processing focuses on, well, processing images. What this means is that the input and the output are both images. An image processing algorithm can transform images in many ways. Smoothing, sharpening, changing the brightness and contrast, highlighting the edges, and so on. Computer vision, on the other hand, focuses on making sense of what a machine sees. A computer vision system inputs an image and outputs task-specific knowledge, such as object labels and coordinates. Computer vision and image processing work together in many cases. Many computer vision systems rely on image processing algorithms. For example, computer vision systems rarely use raw imaging data that comes directly from a sensor. Instead, they use images that are processed by an image signal processor. The opposite is also possible. It wasn't common for an image processing algorithm to rely on computer vision systems in the past, but more and more advanced image processing methods have started to use computer vision to enhance images. Face beautification filters, for example, use computer vision techniques to detect faces and apply smoothing filters, such as bilateral filters, selectively. They can do more advanced stuff, such as enhancing eye clarity or emulating a spotlight by detecting facial landmarks and tuning the images locally. I know the result you see on the right doesn't really look good. It looks very artificial. I did it on purpose, though, to show the difference better. Another key characteristic of computer vision is the use of machine learning. We have talked about machine learning in the earlier videos, but if you're not familiar with the concept, it's a field of study that focuses on teaching machines how to perform a certain task given a set of examples. For example, we can build a model that can tell the difference between a cat and a dog after being trained on pictures of cats and dogs. It's true that computer vision heavily relies on machine learning, but that's no longer a differentiator. Many advanced image processing methods also use machine learning models to transform images to accomplish a variety of tasks, such as applying artistic filters to an image, tuning an image for optimal perceptual image quality, or enhancing details to maximize the performance for computer vision tasks. It's worth mentioning that there isn't really a hard line between these two fields. The line between computer vision and image processing gets blurry when you do pixel-to-pixel transformations. Let's take semantic segmentation as an example. If a model produces per-pixel labels for an input image, then its output can be considered as an image. In that sense, the model will be doing some sort of image processing. On the other hand, since such a transformation involves image understanding, trying to understand what's in the input, it would also be considered computer vision. Overall, I think I would still consider semantic segmentation more of computer vision than image processing, but you get the idea. Another example of the interplay between image processing and computer vision would be the use of convolutional neural networks, or CNNs for short. CNNs typically take pixel intensity values as inputs and learn to process them in a way that makes it possible to accomplish a certain computer vision task, such as image recognition. The output of such a model can, for example, be a label that describes what's in the input image. Internal layers of CNNs can be considered as image filters with tunable parameters. Therefore, what a CNN does can be considered as some sort of adaptive image processing. The use of CNNs is not limited to image processing, though. They can be used to process and analyze other types of data as well. CNNs do a great job at vision, audio, and even natural language processing applications. Researchers and engineers have built amazing applications using CNNs. If you want to learn more about how they work, check out my earlier videos in the Deep Learning Crash Course series. Alright, that's all for today. I hope you liked it. Give a thumbs up if you liked this video. And yes, I did get a short haircut. I hope you liked that as well. If you have any comments or questions or recommendations for my next videos, let me know in the comments section below. Subscribe for more videos, and as always, thanks for watching, stay tuned, and see you next time.